How are we doing today? Today we're continuing on in bonding with our favorite topic called molecular polarity, or the polarity of molecules. All right, you've been introduced to polar bonds and nonpolar bonds. We're going to now start going into whether a molecule is polar or nonpolar. All right, but before we get there, we have a bell ringer. I think we have a bell. There we go. So it says, explain in terms of electrons why the bonding in NaCl is ionic. All right, so this is a question that has appeared on the Regents a few times, and people always have issues with it because they never answer it this way in terms of electrons. They always answer it in terms of electronegativity difference. They'll give me the electronegativity difference of sodium and chlorine, say it because of that it's ionic, which is a true statement. All right, but it does not answer the question, so I cannot give you credit for it. So for the only acceptable answer for this one in terms of electrons, so you can say, simply put, electrons are transferred between the sodium and chlorine. That's the easiest way in and out. Okay, you can say the sodium loses its one valence electron to fill chlorine's electron shell or valence shell. You can say chlorine takes the one electron from sodium. You can say chlorine takes sodium's electron. Sodium donates its electron to chlorine. Some version of that, but the easiest way is just to say it's transferred. Then you don't have to know which atom gets what. But remember, the more electronegative element, which in this case is chlorine, is going to take the electron from sodium. All right, so here we go. What's a molecule? A molecule is things that are covalently bonded. All right, remember, how do we know if something is covalently bonded? We do electronegativity differences. We're not going to get into 3 or 4 element covalent compounds yet. That's for organic, but for right now, it's just when you have 2 elements, you do electronegativity difference. If it's less than 2, it's covalently bonded. Remember, if it's less than 0.4, it's non-polar covalent bond. All right, so molecules can be polar. So this is not terminology that I come up with. I would never come up with this, but this is for whatever people, supposedly smarter than me, I guess, chemistry people back in the day, came up with this term polarity of molecules, and then they use the term polar bonds and non-polar bonds. They do not mean the same thing. And this is one of the biggest things you have to get straight in your head. A polar bond is a bond where the electrons are not shared equally. A nonpolar bond is a bond where the electrons are shared equally. Think of our dog analogy, the 2 same-sized dogs. All right, polar molecules and nonpolar molecules are kind of related to that, but it's not the same thing. All right, the polarity of molecules, all right, is completely dependent upon the 3-dimensional shape of the molecule. All right, and I'm going to be flipping back and forth between notes and my camera today to try to help out to explain this. All right, so we've been drawing all of our dot diagrams in 2 dimensions. All right, like an X and Y axis. All right, we have to add the Z axis, which goes forward and backwards, and I can tell you that it changes some things. Let me get some background stuff in, and then we'll go from here. All right, so here's a statement that may or may not help later on. Right now, it probably means nothing to you, but molecules are only polar if they have polar covalent bonds. All right, so the only way that you can get a polar molecule is if it has a polar bond. But the same cannot be said for nonpolar bonds. So if you draw, so there's 2 ways to think of this. You can draw it in terms of symmetry, or you can do it in shape. All right, I'm going to try to show both of you. All right, but basically, if you can isolate all the positive side of the molecule on one side of a line and negatives on the other, then it's considered to be polar. So what that means is if you have a positive side of the molecule and a negative side of the molecule, you're going to have a polar molecule. Think of poles, like the North Pole and the South Pole. Those are opposite things. All right, so a polar molecule is going to have opposite things. It's going to have a polar side to it, a non-polar side to it. And if we can draw a line to isolate that, then we have a polar molecule. All right, a dipole is a chemistry term, and di prefix means 2. It just means something with 2 poles. So this means a molecule that has a positive and negative side. All right, so anything that's a polar molecule will be considered a dipole, and we might talk about dipole interactions and other things like that later on. But right now, just the terms. All right, and it'll you need to write it down, think about it. All right, and it'll make more sense as we go through stuff in the unit. All right, so to sum this up, a molecule can either be polar or nonpolar with respect to its charge. So molecular polarity. So a molecule can be polar or nonpolar. Bonds, which are different, can be polar or nonpolar. All right, so we're talking about 2 different things. All right, we need to know if it's a polar or non-polar bond to determine if it's a polar or non-polar molecule. All right, but they are not the same thing. And this is one of those concepts that gives people a little bit of an issue if they don't turn their brains on when they're listening today. Okay, how we doing? Just want to go back into molecular polarity here, and I need this camera to show you some. All right, so I'm going to leave kind of a green background on here, so it's not too bad. And we're going to talk about molecules being symmetrical or asymmetrical, meaning polar and non-polar. All right, so I have this kind of blown up pretty good here. I apologize about this thing over here, but I can't get it to come off, so we'll deal with it. All right, so here we got a molecule that is, both of these are the same molecule. All right, just kind of they're visualized differently. You've got water in both of these. You got an oxygen and two hydrogens. This one shows water with like kind of quote unquote long bonds, and this one shows water with short bonds. It is really the only difference. Okay, but the important thing about this, or what I want to show you about this, is in terms of symmetry. So if we look at the particle like this, and I'm trying to orient it so that it looks just like it. So, and I'm going to do the same thing with the other one of water. We're looking at it from this perspective. It kind of looks like it's symmetrical. All right, like that's got a mirror image left and right, and it would be the same top and bottom. All right, but if we turn it like this, or we turn this molecule like that, now it's definitely not symmetrical. All right, you'll see that from the top to bottom in this case that they're not symmetrical. They are symmetrical side to side, but top to bottom they're not. So these would be what we call polar molecules. And this becomes important when we deal with dot diagrams. Looking for a piece of paper. So normally we draw a dot diagram of water to be like this. So if we draw oxygen, oxygen is in the middle. It's got its 6 dots. And then it comes in with its 2 hydrogens like this, and it looks like that. Some people get in the habit of drawing water like this, which if you're asking the question for the dot diagram for water, both of them are okay. This one looks like this, and then this one is looking at it from this perspective right here. All right, but realistically, you have to understand that it looks like this. Okay? All right, so that's kind of the basic structure in there. With that, I'm going to come back to a little bit simpler molecules, these ones. All right, and my desk isn't level, obviously, because they roll that way. You have 2 different molecules here. You have the one on the left and one on the right. The one on the left would be a symmetrical molecule, which would make it nonpolar. And the one on the right would be an asymmetrical molecule, which makes it polar. Okay, so these are, even though they look similar, the color matters. And the color green in this model's kit means a halogen, and the white one means hydrogen. So the one on the left is a symmetrical molecule, which would make it nonpolar. The one on the right is an asymmetrical molecule, which would make it polar. All right, so I just wanted to bounce to that. Now we'll bounce back to the notes. We're going to go back and forth in this today. So assigning positives and negatives to atoms. All right, so the atom that's got the higher electronegativity, so you would know what the elements are, is going to be negatively charged or partially negatively charged. The one that's positive, or the higher electronegativity, or lower electronegativity, is going to be the positive one. So higher electronegativity is negative, lower electronegativity is positive. Asymmetrical charge distribution. So what this means is it has no symmetry, or it lacks symmetry, and especially with respect to charge. All right. So what this means is you're going to get a negative end and a positive end to the molecule. If we look at these particles in 3-dimensionally, this would be asymmetrical charge distribution. You got a negative end, which would be the green side, and you got a positive end, which would be the hydrogen side. All right, this particle would be asymmetrical in terms of charge distribution as well. You get the red side, which would be negative, and the white side, which would be positive. All right, but what that asymmetrical charge distribution means is that you're going to form a polar molecule. Polar molecules can only be formed if they have polar bonds. All right, remember the polar bond and polar molecule are not necessarily the same thing. All right, symmetrical charge distribution means they have the same charge on the outside. So it's an equal distribution of charge. And that charge can be negative and negative, positive and positive, or neutral and neutral. All right, it just has the same charge on the outside. All right, and if they do have the same charge on the outside, you're going to form what's called a nonpolar molecule. All right, it's going to form a nonpolar molecule. So it's going to look like it's quote unquote symmetrical. So now I'm going to go through a couple of examples just to kind of show this. So the first one up is going to be, I have it listed here as silicon dioxide, which I'm also going to use the same molecule would be for carbon dioxide. Silicon and carbon are essentially interchangeable. All right, so if I look at that, so silicon dioxide dot diagram or diagram looks like that. In reality, it looks like this right here. All right, let's see if I can just make this bigger. All right, it looks like this right here. All right, so you got the silicon, you got oxygen, oxygen, there's double bonds, and then there's a double bond. There's two double bonds there. So now we'll go back to our notes, I think. See if I can do it this way. I'm learning how to navigate quickly. All right, but this bond between silicon and oxygen is polar, which means it's greater than 0.4 electronegativity difference. The oxygen is more electronegative than the silicon, so the oxygen is going to be negative, and then the silicon is going to be positive. So what happens is the silicon and the oxygen here form a nonpolar molecule. So looking here, all right, it's symmetrical this way. So it looks the same on both sides. I gotta tip my hand the right way. And it's symmetrical this way. All right, there's gonna be, if this thing's spinning three-dimensionally, you're only gonna see the red spheres on the outside. So it's going to be a nonpolar molecule. All right, and it says nonpolar under there. It'll come up again when you'll see it when it's done. HCl, all right, is a polar bond. Chlorine being more electronegative than hydrogen. So the chlorine's going to be negative, the hydrogen's going to be positive. All right, because we can isolate charges, or we can get a positive charge on one side and negative charge on the other side, we can do that by dividing it in that direction. All right, we would make this a polar molecule. All right, so that's our second one if we want to see that here. So that's our silicon dioxide. I'm going to push that off the screen. Our HCl molecule looks like this. All right, whether you're looking at it like this, if this thing is spinning three-dimensionally, and I know it's kind of hard to see it on here, all right, you're going to see both green and white, which means that you're going to see two different things, which means it's asymmetrical, which means it's going to be a polar molecule. Okay? All right, our next molecule, you guys know this, NH3. Hopefully you recognize by now that it is ammonia. We've talked about it a couple of times. All right, ammonia has this shape drawn two-dimensionally as a three-dimensional object, if that makes sense. All right, I'm going to show you on here. All right, this is what ammonia looks like in the sticks and spheres. All right, but if we were to draw the dot diagram for ammonia, you've got nitrogen with 5 dots. You've got hydrogen that comes in with each of its 1. So this molecule looks like this three-dimensionally. And then if we draw three-dimensionally in 2 dimensions, it kind of looks like this. So you can see that all 3 of these things mean the same thing. And you have to come to realize that these unbonded electrons up here get in the way. If those weren't there, this molecule would take on, I can pull it apart, would take on this shape, which is still kind of triangular, but if you look at it in this perspective, it's flat or planar. All right, but because those electrons are there, it shifts it down because electrons are negatively charged. They don't like to be near other ones, so they're going to spread out. So this NH3 is going to look like this. And because it's like this, you can isolate the charge top and bottom here. You get negative on one side, positive on the other. All right, because you can isolate that charge, it is a polar molecule. All right, so you got examples here. All of these have polar bonds. So depending on the shape and how they're arranged, determines if it's nonpolar in the SiO2, polar in HCl, or polar in the ammonia. All right, so now what we're going to do is we're going to go through the 4 main shapes that you guys need to know, which is linear, bent, pyramidal, and tetrahedral. And you've seen 2 of them up here. These 2 are linear, and this one is pyramidal. All right, and we're just going to kind of go through some examples of these, and then we're done with polarity for today. All right, so linear. These shapes can be polar or nonpolar depending on what's bonded with it. All right, depends on, realistically speaking, if the bond is polar or nonpolar. If it's a polar bond, it's got to be a polar molecule for linears. If it's a nonpolar bond, then it's got to be a nonpolar molecule for linears. It's the only shape that's like that. All right, all diatomics are nonpolar because their electronegativity difference would be 0. All right, so here we go. We got carbon dioxide. All right, carbon dioxide takes on this shape right here. It's carbon double bonded to an O, carbon double bonded to an O. If we look at our thing here, this represents carbon dioxide. All right, you got carbon double bonded to an O, carbon double bonded to an O. All right, so therefore, because these bonds here are polar, these bonds here are polar, so it could be polar or a nonpolar molecule depending on its shape. But because its shape is symmetrical, it's going to be a nonpolar molecule. So in this case, the linear is nonpolar with a polar bond because it has 3 elements in there. Hydrochloric acid, all right, is HCl. All right, chlorine's going to be negative, hydrogen's going to be positive. We can divide it down this path right here and isolate the charges. So therefore, it's a polar molecule. All right, please be thinking about this stuff, not just writing it down, because it's the only way you're going to retain any of this information. All right, and HCl, another representation looks like this. Bent molecules are always polar. All right, what's a bent molecule? All right, I showed you one. You need to know water is a bent molecule. All right, whether it's that shape or whatever other molecule it is. All right, if it's a bent shape, then it's going to be a bent molecule. So we're going to talk about dihydrogen sulfide, which is similar to water, except for it replaces the oxygen with sulfur. All right, bond is polar here between sulfur and hydrogen. So sulfur is going to be negative, hydrogen is going to be positive. If you look them up, you can look them up. All right, and because you can isolate the charge in this plane right here, negatives on one side, negative on top, positive on the bottom, it's going to be a polar molecule. Sorry, that little Google thing stays there. Okay, so that's linear and bent. That's 2 of our 4 shapes that we need to know. Next shape is pyramidal. These, like bent ones, are always polar. If you get a pyramidal shape, it's always polar. What does pyramidal look like? Pyramidal looks like this one down here. I can kind of see it. All right, is this shape right here. Up here is 2, and a lot of times what I will do is I'll put this stick in here to kind of represent there's 2 electrons here, but they're not bonded to anything. It's called unbonded electron pairs. All right, and it has to do with this big fancy thing called valence shell electron pair repulsion thing. All right, but that's what gives it this pyramidal shape versus that planar shape that would make it look like this. All right, if you look at it like this in that dimension right there. Okay, all right, but the bond is polar between nitrogen and hydrogen. I don't know why I put diatomics there, I apologize. Nitrogen trihydride, which is your ammonia, which looks like this. The nitrogen is going to be negative, the hydrogen is going to be positive. You can divide it down in the middle like that to isolate the charges top and bottom, which makes the molecule polar. All right, tetrahedral. Tetrahedral is a fancy shape. It kind of looks like ammonia a little bit. I'm going to show you 2 tetrahedrals here in a minute. So right here, we'll make it bigger. You've got this tetrahedral one and this tetrahedral one. I will tell you one of them is polar, one of them is nonpolar. You should be able to tell at this point in time which one's symmetrical and which one's asymmetrical. All right, but in this picture right here, the one on the right is considered to be nonpolar because it's symmetrical all around. The one on the left is considered to be polar because this atom out here is different than all the other ones. So it's going to allow it to be, or it's going to make it be asymmetrical. All right. So carbon tetrafluoride, which was the one on the right that I just showed you. All right, looks like this. It's carbon with 4 fluorines around it. Because fluorine's more electronegative than carbon, they're all going to be negative for the fluorines. So when you see this molecule, in any way you cut it, it's always going to be negative on the outside. You're never going to see any other charge. So it's considered to be nonpolar, even though it has polar bonds. All right, so that's one of those rarity things where it's got a polar bond, but it's a nonpolar molecule. Now, the only way that you can take a tetrahedral molecule and make it be polar is if one of the 4 things on the outside is different than the other. So in this next molecule, fluoromethane, it looks like this. You've got 3 hydrogens and 1 fluorine. Because they're not all the same thing on the outside, this is asymmetrical, which makes it a polar molecule. Okay, I will tell you, polarity is one of the more challenging things we're going to deal with all year. You have to put your brain to work thinking about it, not just writing stuff down. I'm going to give you some practice drawing some molecules tonight and see if you can do it. All right. Other than that, have a great day. We'll talk to you next week.